particular seminar. I'm happy to introduce one. He was an undergraduate in the there, and I knew him when he was a TA for me and what OT said. So introductory meeting. And so I had to line again, and that was pretty fun. And he went off to NYU, and he's been, I guess he's done a trajectory from
math to ML.
Adversarial learning to non-adversarial learning of robots.
Absolutely. Yes. Thank you, Leslie, for the very fun introduction. If I were to introduce myself, I'd probably be a little bit more generic, and I'll say that, hi, I'm Mahi. I'm a fifth-year PhD student at NYU. I work with Professor Lerrel Pinto, and I really focus on robots deployed in just real-world, messy, unstructured environments. And this is a project that I'm going to be talking about today that is really close to my heart. It's what we call robot utility models, or RUMs. And this project came out about less than a month ago. So if you have any questions, hard questions, please stop and feel free to ask. I'd be happy to give it a little bit more informally with a lot of Q&As in the middle. So this is robot utility models. This all starts with something you probably have seen in social media, right? There is all kind of very fancy robots going around, and people are posting about it. They're like, oh, these are all end-to-end trained policies, and they're going to be soon in your home doing all the things that you'd like to do. And this is a crazy promise, right? I started my PhD, let's say 4 years ago, and even then I could not have imagined seeing something like this at 2020. This promise is actually so crazy that every time a company puts a video like this on social media, the majority of the comments go something like this. This is a guy in a suit. Right. No, so 1X, the company which is making these robots, I don't know if they're actually putting guys in suits because they're a startup and you never know about, what's the secret. There's no paper telling you the secret to making robots look like guys in suits. But we can look at other works recently that has come out to understand the limits of end-to-end learning. Right. So this is another work. This is called Aloha Unleashed. This is from Google DeepMind. And they show very nice demos, for example, tying a robot's shoelaces. A lot of us have actually seen these videos. Some of us have actually also looked at the paper, and you can see kind of details behind it, right? So for example, you can see that for this shoelace tying task, for an easy and messy setup, the success rate is around 70 to 40%. And the total number of demonstration is about 5,000, right? So the question that I'm interested in today is kind of, how do I take something like this, right, a shoelace tying policy, let's say, and put it into my home so that I can tie my shoelaces? Again, to understand that all of this demonstration that you're seeing are coming from this one square table that exists in somewhere in Google's office, and I want to take it out there. And this is kind of a big question in, let's say, imitation learning, end-to-end policy learning that we don't think about often enough. Is, for example, this is something that we trained in 2022. It's kind of at that point was the state of the art in conditional behavioral cloning, right? So you're saying the robot to open up, let's say, the oven drawer, and it's trying to open the oven drawer. Great. But what happens when things change a little bit, right? And here's, for example, we've added a little bit more distractors to the scene. We've added like a little toy blocks, and this completely throws out the robot. Again, this is from 2022, so not that far ago. We've literally changed nothing that is relevant to the task. It is really completely orthogonal. Even then, it is relying on all the features in the scene that you can see. Just this very small difference leads to basically no generalization whatsoever, right? And the classic solution to this problem is, you go and you collect more data, and you collect more data, and you fine tune, and you have a new model that maybe probably solves this task. This is the status quo right now in robot policy learning. Any environment where you're trying to evaluate your policy, you have to add more data. But is it happening in everywhere in machine learning? And I say that's not the case, right? The expectation for modern machine learning has very much been zero-shot behavior, right? So for example, here is, let's say you're a cell biologist. I don't know if this is exactly what it looks like, but you're a cell biologist. You take a picture of your cells, you throw it to, let's say, segment anything as a model, and it can segment out the cells pretty easily. Right? You don't have to worry about it. You don't have to fine tune on your data set anything. Same for, let's say I want ChatGPT to write an email for me. I don't have to fine tune it on a bunch of my email inbox. I can just ask, how do I write this email? And it just works. So the question is, how do we get capabilities like this into our robots, into our robot policies? So by the end of this talk, what I'm going to be showing is going to be looking something like this. This is me hauling a robot in the streets of New York, right? And we take it, we put it in an Airbnb. Sometimes I have to carry it over 6 flights of stairs because that's my fate. But once we do this, we can get zero-shot performance from this robot to these few tasks that we've trained it to do. So here's going to be showing door opening, drawer opening, and a few more simple tasks. But I want to ask at this point, is the goal of this project clear? Cool.
You want to be able to open any door in any kitchen.
Eventually, yes. Again, we're not going to be claiming that's what we're doing right now, because again, there's a bunch of hardware limitations.
The goal, you asked
Yes.
the goal was clear, so I'm
Yes,
trying to-
eventually.
I'm trying to answer your question.
Yes, yes. And not just doors, but you can train policies, robot policies that you can deploy in new environments without having to fine tune it on more data. And the recipe I'm going to be talking about is going to be somewhat traditional, somewhat not, but it's going to be following more or less the imitation learning pipeline. We collect data, we train a model, we deploy it. So let's just get into it. Step one for this, again, is collecting data. And the way we do it is using a tool that looks something like this, right? This we call lovingly as a stick, because this initially started off being a trash pickup stick, but then we stuck an iPhone on top of it. And what I say is that you collect 1,000 demonstrations from 40 different environments to solve your task. One clarification is all the policies I'm going to be talking about are going to be very much skill specific. So it's not going to be one multi-skill policy, but one policy for each skill, let's say. We scale up the data collection by adding an iPhone Pro, which I take out of my pocket usually. And if you look closely, it's really broken and battered just because it's a working phone. And I put it right on top of the stick like this. That is your data collection tool. There is no more intelligence in this except for the iPhone. The rest of it is analog. And you can build this for about $25 to $30, except for the iPhone. But once you have this, the nice thing about it is that you can get very high quality data just from this handheld tool. So for example, here as I'm showing open loop replay of the data that we've collected, right? So on the left, you can see what the demonstration looked like from the perspective of the iPhone. On the right, you can see what it looks like when we're open loop replaying it. And the reason why I'm showing this is that I'm showing the motion data that we've captured just from the iPhone is actually very precise. I'll show another video after this, which will show it more clearly. So here's another example where, here's another example where the robot is trying to pick up some screws. So the two different views of the same thing happening. Again, this is a running open loop. We just place the screws in the same position. But the idea is that just because you've captured the data with an iPhone, now you can very much open loop replay the 6D pose and positions you've captured. And that data, hopefully you can train a policy on top of as well, right? So here's the robot picking up two screws, putting it in a little box, and then picking up the box, all open loop. But once you have this nice high quality data coming from the iPhone, especially given the nice cameras, RGBD, pose, position that we're getting at very high frequency, you can deploy it on different robots, right? So here's the different robot setups that we have. One's on the Hello Robot Stretch. Another one is on a X-arm. But the nice idea is that everything down from the camera looks exactly the same. So we don't have to worry too much about the embodiment transfer. You can just take data, train a policy, and run it on the robot right out of the box. And the reason why we're saying that, 1,000 demonstrations, 40 environments, 25 demonstrations on each, is because we had a previous work where we're trying to train few-shot policies with 25 demonstrations in a new environment, where we showed that a very small, simple task, let's say something that takes 5 to 10 seconds on this tool, you can fine-tune a policy and run it on a new environment by just having 25 demonstrations. So that's kind of the baseline that we start off. So once you have the data set, do people have questions about that? Moving on to how we can train a policy out of it, right? And again, here's where things start getting interesting, because when you're trying to train a policy on large data sets, that's something that you have to be kind of mindful of. So one of the key properties of large data sets that you're trying to train models on is multimodality. What do I mean by multimodality? Let me explain a little bit more. So imagine you're trying to collect some data on opening this door, right? So what you can do is you can take this tool and you can try to collect some data on opening this door. You go to the handle, grab it, pull it open, right? Great, 25 demonstrations collected. Now, let's imagine that you want to increase the diversity in this data set that you've seen. So what you do is you hand this tool off to your friend and ask them to collect some data as well. And what they do is, as you can see, the door is cracked open slightly. So what they do is they go around, right, wedge the tool in the grab, and then pull it open. So it's two different ways of opening the door. Both of the different ways of opening the door is actually very valid. And you want your model to learn from both of those, right? You don't want to just say that, oh, I filter out the data set and I only create this one possible way of opening a door. Which this essentially means is that there is multiple possible right answers for one query, right? Or one observation. If you're starting from a position, there could be multiple right actions. And this is what we call here multimodality, or existence of multiple modes in your data set. This can become a lot more complex if you have a larger data set, because now you're asking a lot more deep people to collect data. And if you're trying to do a diverse set of tasks in diverse environment, there might be just naturally different ways of doing it. One other thing is that the multimodality might not be very clear on when or where you're trying to do. So it might not be as clean of a two possible forks in the path. It could be that at every step that you're taking, there might be multiple possible right answers. And it could be that there are, for example, different orderings of the tasks that you can do. So here's, let's say, opening microwave, turning knob, and opening oven. So here's one robot doing it in one possible way. But there could be a different way of doing the same thing. There could be, you go in the opposite order. You open the oven first, then you turn your knob, and then you open the microwave, right? So all of these are valid ways of going about solving the same problem, but there are different ways of going about it, and your data set is probably going to be capturing all of it. So you want a policy or policy class that can actually capture all this multimodality that exists in your data. There are different solutions to this. We work on something that is more inspired by language modeling. Our friends at Stanford and some friends at MIT and TRI work on something that looks more, image generation. So we're going to be talking about what we do. We try to capture this as a sequence modeling problem, right? This is standard for many modern policy learning algorithms. You have a sequence of observations. You're trying to predict actions at each time step. And if you squint a little bit, right, you can see a similarity between this and, let's say, the language modeling problem, right? Where you're given a sequence of tokens, you're trying to predict the next token. Again, I'm saying you squint a little bit because it's not exactly one-to-one. There are a lot of differences. But one of the nice things is that you can observe how, let's say, language models are doing it. And you see that they're handling this inherent multimodality in large data sets by actually predicting the probability over different tokens. Here, for example, if you say, I saw a cat on a blank, right? There could be multiple right answers. There could be, let's say, mat with 76% probability, bed with 12, and tree with 2, right? All of these are valid answers. All of these are correct. And what you do at the end of the day is you sample from this distribution to generate different answers. This is one possible way with one very small caveat, which is the actions that you're trying to predict over, those actions are continuous. Right? Generally, for example, in this tool, we're trying to predict over 6G pose and position. We have one-dimensional gripper value. None of this is actually discrete. So you can just predict, let's say, a categorical distribution and sample from that. So what do you do? So in this work, what we do instead is that we try to tokenize the actions that we have into discrete tokens. We use this very standard tool in generative modeling called VQ-VAE, right? This started from this paper, which was trying to generate images with VQ-GAN. The high-level idea is that you take a continuous signal and you tokenize it into buckets or discrete tokens, and then you generate Y sampling from the same categorical distribution. Looks kind of similar to VAEs, if you're familiar to VAEs. The only thing that is different is that you are trying to enforce that your latent is sampled from this fixed set of possible latents. Right? So you call this an embedding codebook. Generally, there are, let's say, 256 or 256 squared for images, things like that. And then on top of that, you do your generation. Nice thing about it is that on the both ends, the signals that you have are continuous. But in the middle, you have a discrete value. And because this is discrete, now it is super easy to learn multimodal distributions over. And this is what we do, the trick that we use to learn behavior from this large-scale datasets with multiple possible correct answers. There are two tricks that you have to actually realize and use to do this properly that probably isn't there for image generation. One is having to do this tokenization in a hierarchical manner. So for example, this is the picture. You can see a two-dimensional action space. We've tokenized in one and we've detokenized it, and this is what it looks like. This is kind of sparse, but one thing you can do is you can tokenize the residuals on top of it, right? So what happens when you tokenize the residuals is you can express, let's say, a little bit more high resolution actions by using more tokens per action, right? So if you use 2 layers of tokenization, you have a little bit more dense action that you can represent with your policy. So this is trick number 1 that we use to increase our resolution, which helps us in solving tasks where some precision in space matters. Do you have any questions about this part? Yes. You can do anything. We use 2 just because it seems to be sufficient for the task we're trying. Leslie.
You're tokenizing, was it 6 off poses or high trajectories, or what are we tokenizing?
You can do either. You can do either. So for example, one of the things, again, we heuristically choose this, but one of the things that we do is, for example, when you have a higher frequency action space, let's say if you have actions at 50 hertz, then you take, let's say, 10 actions at a time, and then you tokenize it. Because it's a VQVAE, you can actually pass in arbitrary length things and then tokenize it. But for example, for actions that are 3 hertz, we tokenize each action, right? All right. So once you have this tokenized action space, you can just model the whole action prediction problem like GPT, right? So you have an observation sequence, you pass it through a sequence model, out comes some sort of tokens that you sample from your categorical distribution. And once you have this, you can train it, for example, by just your frozen encoder that you have learned. You have some ground truth tokens, and you can compute some sort of categorical loss on top of this to train this model. For sampling from this model, right, you sample the discrete tokens that you have coming out of your model's categorical distribution, and you decode it, and you get, let's say, multimodal actions out of your model. Yes, there's a question in the back.
So the sequence, do you think you use a lot of structure by because, for example, classically you have a continuous property using the MSC, where like if you're actually a little bit, like say you get into the distributed division.
You have predicted the next 2 slides. Great. Yes, I love when that happens. Yes, exactly. So one of the other tricks that you have to actually use is that there is a lot of difference. For example, if I'm trying to go for this bottle, if I slightly bump it and knock it over, there is a huge problem in there, right? And when you're discretizing, as you said, you might be losing out on some crucial part of the signal. So what we do is we add an auxiliary loss for modeling the continuous offset. What do I mean by continuous offset? Let's say that I have a continuous variable and I'm modeling with some number of discrete bins. There's always an offset between what you've recovered and what you initially put in, right? And again, as you increase the number of bins, this offset becomes smaller and smaller, but it doesn't quite go away ever, right? So the second detail that you have to pay attention to when you're trying to use this architecture is you have to model this continuous offset. As it turns out, for, let's say, the more precise the task that you have to do, the more importance this continuous offset has. But one of the nice things about it, generally doesn't determine quite which action mode you're going to be falling into. It's really about making the very small correction that you need to make your action precise so that you can execute it on a real robot.
I guess it's also having sort of prediction because you're bounded in possible.
Yes. So for example, when you do a 2-level prediction, right, you predict the first token first, and then you predict the residual token last second.
Yeah.
And then once you've given both of those, then you can predict what's the continuous residual off of that. Yep. I'm sorry, I don't think I understand. What is the residual? What does that mean for residual to look like something? Mm-hmm. Mm-hmm.
And your discrete bias of the
right.
And then so I assume that the particular offsets are there, so at the back
Mm-hmm.
to the discrete bias vectors.
Mm-hmm.
So how does the end predictor look like after you add those particular offsets back?
I mean, how much error is there?
I mean, you can train it to have arbitrarily low loss. We found that there is some importance in balancing this out. because you're kind of mixing together something that is a categorical loss with something that is a continuous offset. And so you do have to balance it out a little bit. But I'm not quite certain what does it look like. Like, are you asking about the magnitude, or are you asking about?
Yeah, I'm wondering if that actually helps.
Oh, yeah. So we do have some ablations in our original paper. So this is called a VQ behavior transformer. In the original paper, we do have ablations, and it does seem to matter for a lot of tasks that we do. So yes, it does matter. And this was actually like the last thing that actually helped us use this algorithm in the first place, because I think other people have tried discretizing these things before. Doesn't quite work because you don't have the residual. This idea comes originally from like bounding box prediction in object recognition. So what you do there is you have like a bunch of bounding box proposals. You propose bounding boxes, but you also move them around a little bit in space. Yep. So this is kind of actually where we take inspiration from. Yeah. And the loss structure that we use is also very similar to that. Cool. But one of the nice things about this is that once you have, let's say, this model where you're predicting, tokens of actions and you're sampling from that categorical distribution of tokens, is that you can start from the same state and sample different sequences of actions that end up in different results. So here's one robot that is trained on opening doors, both doors, from the same starting position. And when you were sampling this, right, starting from the same starting position, this is opening the left door once and the right door once. And this is something that we really like, because then it's showing that it's actually capturing the different modes of behavior that we see in the data set. Another nice thing about this architecture that we like is that because it's just making a singular pass through our model, it tends to be faster than diffusion policy while having kind of similar level of modeling capacity. So we're not losing too much on the precision, and often it's kind of like neck to neck. But in terms of speed, when we're trying to run it in the real robot, when we're trying to run it on the robot CPU especially, this tends to be much faster, which is, again, crucial for us. And also, by the way, all the policies that we're running are running in the robot CPU. It's like an Intel Celeron little box and running at like 3.75 hertz. Cool. So this is kind of the model learning part. Do people have questions so far? All right. So then I will move on to the deployment part of things. So how do we take, these policies that we've trained on, let's say, 40 different environment data, and how do we put it on the real robot and get it to work in arbitrary new environment? Again, important part is that we're not using any new data. We're not doing any fine tuning. So setting up the evaluation environment is kind of interesting and important. So for example, what we did here is we ordered off a bunch of drawers from Amazon, and we set them up, and we're like, okay, we're going to put it in random places. Some environments are kind of like in our lab. We just didn't use any data that we collected in our lab, so wanted to have it going. Again, for a simpler task like tissue pickup, we just really put it in weird places in our lab. Again, consistently for the same evaluations in the same places, but these are just, very random cluttered environments that we just dropped it into. And again, grounding our expectation, right? This is what we saw 2 years ago using very similar algorithms. Now we're just training it on more data. We're a little bit more conscientious about how we're collecting the data, and we want to run this. And as we run this on this, unseen environments, this is what the plot looks like, right? Kind of the models that we've trained, we can just download this, let's say, off of the internet for anyone who has a Hello Robot stretch. And, we can expect a success rate of average 74.4%. This is great for us doing robotics, right? We're like, wow, 75%, this is amazing. All right, we can write a paper, we can go home. We have an advisor, Sumit, who works at Meta, and he was like, okay, this is great, but if you want to build on top of this, right? If you're trying something, let's say you're trying to build a long-term policy out of it, you'll have to do better than that. And we're like, oh no, how do we do better than that? One of the things that we did do at this point was we tried to understand how this thing is failing, right? It's like, okay, 75%, but the number doesn't tell us anything. How does this thing fail? So one of the things that we do in the first place is, like run it in random places, and we see, okay, when these policies that we're training and running it in arbitrary environments, a lot of the failures are not really what we'd call like destructive failures, right? It's not like, oh, we've like spilled something on a table and now a human has to come and clean it up. It's really, oh, I thought the handle is here, so I tried to grasp it and pull it, but the handle wasn't there. Or for example, oh, I tried to straighten up this bottle and then the bottle just fell off my hand. But one of the nice things is that if you could have, let's say, an angel come and tell you like, oh, actually this bottle fell off from your hand, try again. you could just do it, try again and see what happens. One of the crucial things that we wanted to do here is kind of like make independent decisions. So whatever is making our policy decisions, action decisions, we wanted it to be different than whatever's telling us, oh, did the policy succeed or not? So what we went over is we just passed in a lot of these images, right? As we're running this, as we're collecting data from the robot's head camera, we passed in a bunch of these images into GPT-4, and we asked, hey, if this thing that we're trying to do, did it succeed or not? Right? So here you can see a bunch of images where the robot went, tried to grasp a handle, pull it open, didn't work out. And again, we are lucky to be living in the time that we're living in, where we can just pass this off to this black box model and it can tell us no. Great. When we know this answer is no, all right, we can just try to reset our robot and run it again. And one of the crucial things from earlier on that comes back to help us is that our policy is somewhat stochastic, right? So the idea is that when you run the same thing multiple times, you could potentially sample different sequences of tokens, which might end up in slightly different behavior. And if some of those behaviors are better than others, by trying it a few times, you actually increase the probability of success. So this is what happens with us, right? If you don't succeed, try again. So we just do this automated retrying with, like multimodal LLMs as a verifier. As you can see here, again, it's from where it failed. After a few steps, it's trying again on both environments, one with drawer opening, one with the bottle reorientation. Do people have question about this piece? Yes.
You showed 3 images on the previous slide. Maybe
Mhm.
we'll go back to it.
Yeah.
But it looked like none of them was the robot actually reaching in and clamping down on the.
So good point. I only showed 3 to illustrate the process, but we actually pass in like 1 image per second.
Ah,
Yes.
okay.
Yes.
Okay,
So
for a total of what like just 30 or.
yeah, it's more like 15-ish,
Okay.
roughly.
Good.
Yeah.
You know whether or not it's going to succeed within seconds.
Right. And one of the things that we do see here is that on average, we only need to try like 30% more times, which is kind of aligned with the fact that we have something that succeeds like, let's say 75%.
You only need to try how many times?
Like on average, we try 1.31 times.
And with that, you get what success rate?
With that, we get, I'll show in one slide. So again, this is just verifying the success. We give the same thing. GPT says, yes, we can terminate. But with that, we get up to average 90%. Yes. And that, helps us a lot. For different tasks, it helps in a different amount. And we can talk later about, where are the cases where it doesn't quite work out. But, with what we started off at 75%, we do a few retries, actually not even that many, only 1.31 retries on average. And we get something that is close to average 90%. And with that, we kind of have a complete package. And what we do is we just package it up. We take it to, for example, different Airbnbs and whatnot, and we try out and we run it. And these are just showing a few videos of different environments, different tasks. On the top left for you, door opening. On the top right, drawer opening. And the bottom left is bag pickup. Again, we tried to just illustrate it. This is not a very complex task. And on the bottom right, we do a reorientation. And we have total of 5 policies. We have them available for download on our website so that other people can download and play with it. And, like that's kind of like what we wanted to set out. So do people have questions up until now? Yes, go. So these are all single task policies. So this is really like, oh, are you running the door opening policy? It just seeks out doors and tries to open it. And so great question. We don't specify that. So if you put it in front of multiple doors, we don't know which door is going to be opening. Yes. Yeah. So I mean, again, this is, like now we have more research on, let's say, like how do we condition different policies, right? So which we couldn't tie into this. But here the goal was very much like, can we train a policy that just tries to open doors? And as it seems, we can get something that is just like door opening crazy. Thomas.
Understand that doors on the tactile handles.
Mhm.
It's just any box still
Are
I-
you picking up the tissue out of the box?
It's
What is-
picking up the tissue out of the box.
So.
Yes.
it's Figuring on the tissue.
Yes,
not the body.
yes. So it's like tissue sticking out, you just try to pick it up. That's again, yes, question.
So, is it, necessary to increase it all the way back to or the way that, like, for example, like, that would be something.
Right. No, I think this is a great question. Here we're just doing a complete reset because we want to be as safe as possible. But definitely you can make it more efficient. Definitely you can do like a better tracking of your state and like how likely you are to succeed if you started from here. So yeah, no, we don't do that, but you can totally do it. Yeah. Question.
Because you have this language model, have you explored leveraging that as a really kind of cooperative research? So for example, you know, say, oh, you missed it by this much, maybe try shifting over here. So if you have like a sentence.
So there are like two things over here. One thing is that I am not sure if the language models are grounded enough to give you such fine feedback of like, oh, maybe move 20 centimeters to the right. I would love to see this kind of experiments if they are capable of doing that. Yeah, I mean, I don't know if the number is grounded. That's kind of my problem, right? Yes. Yeah. Yeah, that's true. That's true. Mm-hmm. Yeah, so for door opening, it's kind of like most doors are opening left or right, right? So you kind of have to just guess like, okay, is it going left or right? Yeah. Mm-hmm. Right. Mm-hmm. Yeah. Yeah. Again, there's like some, let's say, stack of 5 frames that we're feeding into the policy. So it has some idea of like which direction it came from and whatnot. Leslie.
Okay, so how do you, well, there's a trivial question. It's not that interesting, which is like, what if I have knobs on the cabinet?
Oh, doesn't work.
Okay.
Yeah.
Okay, then the next one is, how much do you retry? Like, how do you decide when to give up?
Yeah, no,
Why
this
does it only get to 90, right? What's the gap?
yeah, no, that's a great question. That's a great question. So what we did was we did cut off at 10 retries. Again, we just hard coded. We're like, okay, nothing more than 10. If you're trying so hard, just give up. Not a very satisfying answer. I do think that, so most of the failures as we see, either they work pretty early on or they do something catastrophic. For example, you drop the bottle and the bottle rolls away and you're like, oh, I can't do anything more. Right. So you very quickly converge to one of these two cases. Or another thing that we do see, for example, is GPT lying to you and telling you you're done when it's not done. So for example, this door, right, with the door on the top left, you see how there are like holes in it. So when you ask GPT, like, is this door open? GPT is very likely to say yes. Just because there are holes in it, it's like open. So it's like, okay, yes, this door is open. And we're like, okay, this is clearly not open. So GPT a lot of times hallucinates and tells you like it's done because it's tired and wants to go home. So yeah, so there's another termination condition. So you know which actions you've executed, so you can just execute the reverse of that. Yeah, so it's very stupid. It's not doing anything fancy. It's, and again, like if you know, like you put your head there, it's definitely gonna slam into you. Yeah. I'll talk a little bit more about what contents matter for the data in a minute. But we don't do, for example, like a lot of retrying in the data collection process. I know that some people have done that and shown success in like the policy itself knows to reset when it's failed.
Yeah, you should think about it.
Sounds good. Sounds good. All right. So the last part of this talk that I'm going to be talking about more is how can you go out and train your own robot utility model, right? Because again, there's a lot of talk around of like, oh, we're just going to train a ton of data and now we're going to be training our own big robot model that's going to be doing everything out of the box. Great, but what are the things that you should be keeping in mind when you're trying to do that? The do's and don'ts of like training a robot utility model is understanding this few parts of the recipe that we found to be important. So first thing that we do find out is don't fuss too much about what training algorithm or policy learning algorithm you are using in the very beginning, right? We have a lot of great options. Pick your favorite, the one you're most comfortable working with. Do collect as large of a data set as you can, right? Don't just give up after collecting 20 demonstrations because your arm's hard. Do ensure that the training data you're collecting is diverse, right? So don't just say that like, oh, I have a drawer in here, so I'm going to collect 20,000 demonstration in this drawer, and then I'm going to have a policy that works everywhere. And when you're collecting this data, it might be very tempting, but don't compromise on the quality of your data. And as I have this 4 suggestions, I'm actually going to be showing you experimental results supporting all the claims that I'm just making. So this is how it goes. The first thing about, as you're collecting more and good quality data, this is decreasing your reliance on policy learning algorithms, right? So here's, for example, diffusion policy that a lot of people are using. We're using VQBet and diffusion policy both, but we're probably a little bit more comfortable using VQBet because that's the algorithm that we've created in-house. But here, as you can see, the performance of different policies on the same data set is pretty neck to neck. It's not that far different. And if you look at the error bars a little closer, there's a lot of overlap. So really what it's telling us is that, oh, maybe, if we tuned it a little better, again, we are not the ones who created diffusion policy. Maybe it would have been the same. Maybe it's a little better. But overall, the performances are pretty similar. More than that, when we used a wider policy class for 2 environments, and all of this is actually experimented on 5 different unseen environments for each task. So, 50 trials total for each of the numbers. So when we did it in 2 different tasks, we see that even very simple baselines, like a 2-layer MLP on top of a ResNet 34, actually works decently well when you have a reasonable data set. And it gets pretty close to, let's say, the action chunking transformer that people are using on a lot of latest applications, right? This was surprising to us because we thought that like, okay, maybe there is a lot to do in policy learning that we're not taking advantage of so far. But it does seem to help when you do scale up your robot data, right? So the second piece is that scaling up your robot data set generally gives you good returns. There's one difference, which is as you scale up, you can see better performance in smaller data sets for some algorithms, like VQBet, which is the green line, does worse in smaller data sets. But as you scale it up, it seems to be that VQBet is doing slightly better. However, the error bars, once again, are kind of overlapping. So again, I don't know if it's enough to draw conclusions from, but it does seem to generally help if you scale up your data set. Some algorithms tend to look like they're saturating a little bit, but again, we have not had enough diverse data to really claim that. But this is something that I'd really want to understand a little better. Again, this lines up with my own priors as well. I do tend to think that diffusion policy maybe puts a little bit more structure or priors, and that would line up with what we're seeing here. The next thing that I want to really reinforce is that it really matters when you're collecting data to have a lot of diverse environments, more than what density you have for different data sets. So here's 2 different illustrations showing 2 different types of data set. On one data set that is kind of like ours, what we do, we have 40 different environments. On each environment, we have 25 demonstrations. It's very kind of on the low end of this policy learning algorithms. And we have 1,000 total demos. On data set 2, we have a lot more demonstrations on fewer environments, right? So we have 5 environments, we have 200 demos each. We end up with 1,000 demonstrations total. But once we compare this on 2 different tasks, let's say, for example, first we try it on door opening. And on door opening, the structure and the physics is maybe not that different. And so the performances are pretty close to each other. But for example, when we're trying to do the object reorientation, right? So where we pick bottle up and try to put it straight, all of a sudden the differences matter quite a lot, right? Here is almost a 50-point drop in what you're seeing from just using the diverse data set to the data set that is more uniform. So I definitely say that like if you're trying to collect data, do try to collect a lot more diverse data than what you've seen so far. And then the last piece, yes, question. The validation is happening on the 5 unseen environments. This is not seen by any data sets. No, this is again somewhat out there. So for each of them, we start from different spatial locations and we do 10 runs. So 10 times 5 different environments, so that's 50. Yeah. Yes. That's a very good question. And I think there's like no very clear metric. We have a little visualization where we're looking at like different dyno features of different environments, and we kind of look at like what are the most distant pairs, let's say. But again, there's no clear answer. The backgrounds, but also like the objects that you're manipulating do matter, right? So for example, if you're trying to do reorientation, bigger and smaller objects act differently. And if it's like half filled with water versus marbles, it will act differently. So there are different dimensions, but this is really, again, a very initial result, I would say, that shows that diversity do matter quite a lot. The last thing we're talking about on this axis is very much the data quality versus quantity. A common practice in robot learning, especially learning from large data sets, is that you throw in everything in the same pot and you try to cook it together and you see whatever comes out of it, right? So to try to understand that, what we did was we created two subsets of our data set. The first subset, we sort all of our data that we collected by time. The first subset that we take is just randomly sampling different environments from this. Okay. The second subset that we take is after sorting by time, we just take the second half, right? So the more recent data. And this is kind of a mental model of as we are going around collecting data, we get better at collecting data. So the data set that is the second half should have more of an expert behavior than the data set that is kind of randomly sampled different environments. Does the setup make sense? Cool. So when the setup makes sense, the first obvious experiment that we run is, okay, having more expert data is better than having non-expert data. Okay, duh. Everyone knew that. However, the interesting thing happens when we put together both of these data set and we train on that. What we see is, for example, some tasks, of course, the performance goes up, and that's great. That's amazing. But on some other tasks, right, the performance is going down instead of going up, which is kind of counterintuitive from our very much like, oh, add more data, add more layer, deep learning kind of way of thinking. But it does tend to imply that we should be thinking carefully about what data we're putting into our training distributions, because whatever algorithm that we have right now may not be able to handle this. And this is actually not limited to just, let's say, VQBed. This is happening across all different training algorithms that we're using. So once we have this is kind of like the guidelines and data. One other thing that I want to point out is this policy that we're training, you can just actually run it on different embodiments as well. So here's the same setup. We're just putting our wrist at the end of an X arm. X arm has 6 DOF control, and then we have 1 DOF of gripper open close. So it's the same control space. And on this, we're running the same policies. And it tends to be working pretty similarly. There's a little bit of a gap, but overall, it seems to be working fine. Do people have questions so far on this set? Yes.
So your policy outputs are keeping hands. What's the output of your policy?
Yes, great question. The output of the policy is delta XYZ, delta rotation, and absolute gripper value. It's between 0 and 1.
I see. And you don't ever get into some singularity of the robot.
No. This is again like very simple tasks. So yeah, so we don't have to worry too much about it. But again, like if you've seen the robot itself, it's very much like, oh, I'm standing here static, and then there's very small rotation happening here. So it's hard to get us into singularities with limited control space like that. But definitely will become a problem, like if we try to scale it up more and more. I'll finish all my slides soon, so I'll take the questions after that. And the last piece that I want to just tell us a little bit, since we have a little bit more time, is, for example, different factors of the self-verification that we do with the multimodal LLMs. So the first thing that we look at is the improvement rate. On average, it's 15.6%. That's great, but as you can see on different tasks, there are different amounts of improvement. Again, the mean tries to success averages out to somewhere around 1.31. The nice thing about me for thinking about it is that if you were to say that like, oh, something succeeds around 75% of the time, then expected number of tries is 1 over that, which comes out very close to 1.33. Nice. Yes.
So, like, you report failures here as
Yeah, because you can imagine this as like infinite,
right?
right? So we dropped those, and we're like, if we're only looking at the successes, which didn't get into a catastrophic area of like, oh no, robot, why are you doing this, right? That's kind of what we're counting. But it's a very good question, because practically this is infinite.
Right.
If you have situations where you can't recover from. Yeah. Exactly. So there's a lot of just hallucination going on when you're trying to pick up bags. especially because the robot camera that we're using to evaluate this is a camera that is mounted on the robot head. So it's like looking down onto the hand, and it's very minor difference between when it's grabbing the bag to when it's lifting the bag. A lot of times, even before it has fully lifted the bag, it says that like, oh, you're done, go home. Right. So there's a lot of weird failure cases around bag pickup there. But yeah, this is again like interesting things to think about, but also think that as these models get better and bigger, right, like a lot of these error cases might go away. Or if you imagine there is a third person camera that you can look at to verify if you've done or not, a lot of these errors might also go away. But this is what we've released so far. Everything that we've released here are open source. These are some fun demos. This is running on one of our collaborators' robot in Pittsburgh. He's actually using a different wrist camera, if you see here. It's an Intel D405. We have to do a little crop to align the two observation spaces, but once we do that, it seems to be working pretty well. There are some differences because, for example, the D405 has a different depth of field than the iPhone, so things get blurry at different distances, and there's a little bit of gap there. But again, it's a non-zero success rate by just someone who has a Hello Robot in Pittsburgh downloading our policies and running it in his home. All of the code that you can see are on the link here. We have a website called robotutilityModels.com. And if you have a robot, or if you have like an X-arm, for example, I can give you a mount that you can 3D print and try this out. So do try this out. Do let us know. And before I cut this off, I want to say that there are more than one way of getting zero-shot robots working in the world. I have this other line of work, which is more using LLMs and VLMs, the representations and some pre-trained skills to chain together. Here's, for example, the robot trying to move an orange to the red plate. Again, the world is changing around the robot and so on. So you can also look into that. This is kind of a teaser, and I'm happy to talk more after the meeting about it. But this is what the zero-shot policies that I'm talking about, robot utility models, the code is there, the video, data, hardware, everything is there. This tool you can print out for $20. And if you have any questions, feel free to please email me. Thank you so much. Please.
Resistance to the expert or non-expert data or its name.
Okay, increase the size of the model or increase the size of the data. That's a very good question. I think size of the model seems to be very irrelevant at this point, because it seems like a lot of things that it's capturing is really the diversity in vision rather than the diversity in control. And it's kind of a chicken and egg problem in the sense that if you want a multimodal model to capture all the possible modes of interaction, then necessarily some of those modes of interactions might be the suboptimal modes of interactions that you may not want your model to exhibit. So I was talking to someone earlier today, and they were suggesting, in, for example, LLMs, you see a pre-training phase and a fine-tuning phase, where the fine-tuning is really to extract the more desirable behavior out of the model. Eventually, you may see something like this here, right? You deploy a robot, it's running around in a home. As it's like interacting with objects, it's learning what are the desirable modes of behavior. So that might be one way to solve it. Did I answer the question?
Yeah.
Cool. Yes.
So I want to ask experience. So what are the things that are really, really difficult, that I really want to do, but it's a little bit challenging?
What would be my wish list? I think the wish list for me goes very much in the direction of, I think we're hitting the limits of what you can do with hardware like these. Two-fingered gripper, flexible on a kind of weak robot that can apply, let's say, 4 pounds of force at the very end of it. So for example, one of the things that I think about is what if we could let's say stack fridge, right? Like you just did grocery and you want to put a bunch of objects in the fridge. And now you can't do that because the robot cannot apply enough force. A lot of these times, this robot is kind of funny too, because it tries to pull open a fridge and then tilts over because all the weight is in the bottom. And so, there are a lot of things that I'd like to do that is kind of hard to do in the hardware framework that we do have. But it's surprisingly capable, right? We're going around for the OK Robot project, we're actually, picking and placing a lot of garbage from the floor and putting it into the right places and stuff. And I think that's pretty exciting. So a little bit more capabilities would be nice. A little bit more dexterity, a little bit more, like a more able robot. Yeah, and I think again, like a lot of people are working on that. So I think this is an exciting time to be living in. Thomas.
So you've got a feedback loop that's taken wrong.
Mm-hmm. Mm-hmm. Mm-hmm.
So most of the work is going to be
Right.
because the actions are relative.
Mm-hmm.
Can you think of a way of kind of increasing the diversity of the group without necessarily trying to bringing it up the stairs before we get to
So two things here. One thing is that we just take this to 40 different departments. We don't have to take the robot, which really makes our life a lot easier than we'd have to. Again,
I mean, it seems like there's isn't there a lot of structure of this?
Yeah. So this is actually an interesting point. So the project that we did last year, right, that we call Dobby, the way we did it is that we did a very strong image pre-training on a lot of diverse data, which really helped us getting down to 25 demonstrations in each environment, right? So eventually maybe we'll break through that limit, but it seems like, okay, even after you have like a pretty strong image representation, you need some sort of variability to understand how to control your end effector. So I think there we've kind of like reached that limit. But for the environments, I do think that there's a lot of options for our algorithms to be better. Yes.
Because it's not like it's seen a lot of.
Yeah. And so, for example, one of the things that I really like about, sorry, where's this figure? Yes, like here, right? And for example, like for some tasks, right, you don't really need to take it to 40 environments. Like door opening, you can be done with 5, and that will give you 64%. That's amazing. But for some other tasks where it does seem like the physics matters a little bit more, it seems like it is important. So there's a little bit of, yeah. Yeah.
Well, right, I mean, this is door opening with doors that have handles that look similar. I mean, if you.
It's like
want
a
to
cylindrical,
make that
nice long.
task a little more clearly. right?
Yeah.
Because.
No, I agree
I
completely.
have coverage around knobs, and so
Yeah.
that's a different story, right? So it's door opening of.
Yeah.
In class
Mhm.
somehow.
Yeah. So
Robotic is combined, well, okay, I know it's against but combining the complexity of the digital
Mhm.
environment with the complexity of the action.
Mhm.
You're reusable environments to kind of replicate the convention.
Right. So we.
Emphasize the vision.
Mm-hmm. So for example, like the last year's project that we did here, right? It's very much like it very heavily relied on amortizing that vision. We had a larger data set that is like a lot more play data. And once you pre-train on that, only then you can get actually a good, pretty quick pickup of a new task or skill or whatever you want to call it in environment. But it does seem like you do need some information in environment of how things move. Other questions? Yes. Yeah, no, that's a very good question. I think the way I mentally think about it is the things you could potentially do with this tool, let's say 5-10 seconds. Again, it's not like a very solid criteria. For a lot of times we are implicitly using force feedback, and the robot does not have force feedback, so it cannot do that. So again, it's hardware limited tasks that it can do with this tool without needing force feedback, let's say. We generally went in and like looked around and we see like what works, what doesn't work.
I think we're gonna officially thank Mahi.
Thank you.
Yay.